Okay, so in this movie clip, we are going to study how to derive the narrow base diode current versus voltage characteristic. So previously, we have learned that kind of a wide base diode current voltage characteristic. So I said a kind of wide base. What does the word of base mean? Going back to the cross-section view of a bipolar junction diode. So let me briefly tell you how look like the BJT is. So BJT consists of two series connected PN junction diode. So like that, there is a single PN junction diode. There is another PN junction diode. If we combine those two separate PN diode into one, then we're gonna build up the PNP BJT. So BJT means a bipolar junction transit oops yeah, transistor. So here bipolar, bi means indicates a two, so two junction. So where does it come from? Yes, here and there. Okay, so we're gonna have a two junction system, and by taking advantage of using two junction system, we may implement the transistor function. Okay, so transistor is basically it has three different terminals, and terminal A to B, the current flow between terminal A and B should be controlled fully by the third terminal C. So in this case, the current flow from P to the other P is governed fully by the C. I mean this N region. Okay, so once hole has been injected into the N side, and that hole has been diffused towards the second junction here, and once hole is been well arrived at the second junction in this region because of the internally developed electric field, which is a built-in electric field in PN junction, right? So this hole would be alive and get to the second P region. So we can say that the current is flowing from P to P throughout the N side. And this current flow should be well governed by how much hole can be alive. I mean, the being alive means these injected holes from the first P should not be recombined with the electrons in the N side, which is in the middle of the P and P junction. So the N side, the how much electrons can supply and how much electrons can recombine with the holes, which is injected from the P side on the left hand side. Okay, so in that sense, you may guess, aha, from P to P, the hole can be injected, and without any recombination with the electrons in N side, that injected holes would be alive and move toward on the other P side, on the right hand side. And this current flow is fully governed by how much recombination event would be happened in the middle of the PNP system. So we can claim that this hole's movement would be fully governed by the recombination event. Okay, so this recombination event would be explained as how much current has been flown into the N side. Okay, so let me redraw the PNP again here. Okay, so the hole is now traveling from left hand side P to the right hand side P, and this traveling would be blocked and controlled by how much electrons has been supplied for recombination event. Okay, so in this sense, the current flow from terminal A to B is fully governed by terminal C. This is a basic function of transistor. So you may expect that the transistor function can be obtained by simply placing single PN diode with another PN junction diode. Okay, so and herein the N side, I mean the physical dimension of the physical length of the N side in the middle uh, would wouldn't be the very long, wouldn't be very super long. So that's the reason why we should go back to the PN junction diode analysis, and we should recall how holes are injected into the N side and how those injected holes can be diffused toward the opposite side of the N side. So previously, when we are studying and doing analysis for single PN junction diode, the holes are injected into the N side on the floor device, and these holes should be diffused out. While it is diffusing out, it is recombining with many electrons in N side. So in the end, once all the holes should be recombined with electrons, and no holes are left at x of, I would say this is x of xn, that is, I would say, x of infinity. Usually this infinity indicates a 5 or 6 times diffusion length of the holes injected from p side. Okay, so the total length for injected holes are, I would say, walking around and or moving forward is long enough to be recombined with electrons. However, in this PNP system, this inside the physical length of the inside in the middle wouldn't be long enough in terms of, I mean, from the perspective of the injected holes. The holes are injected into the inside, and that all the injected holes should be fully recombined with electrons in the inside. However, because this physical length of inside in the middle is not long enough, so part of the holes would be still alive and get to the second p side here in. Okay, so what if all the injected holes are recombined with electrons and nothing can be delivered to the second p side? Then we may not form the current flow from p to p, then which means that no current flowing. So now we should fix and modify the boundary condition for deriving IV characteristic. Previously, when we are doing the analysis for ideal diode current versus voltage plot, all the holes are injected, and all the holes injected holes should be fully recombined with electrons in N side. That is the main reason why we are saying that at the edge of the N side, away from the depletion layer, so delta P sub N at x is infinity, it should be 0. So excess hole concentration in the N side should be 0. That was used to solve the second order minority carrier diffusion equation. However, now this physical length of the N, when we are taking into account the PNP system, this physical length is not long enough for all the injected holes to be recombined with electrons, so that delta P sub N at x of, at the opposite side of the opposite edge of the N side shouldn't become 0. Okay, so going back to the following boundary conditions, we used this condition, those two conditions. So let me summarize and let me make it clear. Okay. Previously, when we are doing the ideal diode analysis, once hole is injected into the inside and those holes are diffused toward the opposite edge of the inside, and no holes can be arrived at this point. But now we're talking about the PMP system, and in the total PMP system now I have captured left hand side image of the total PMP system. So you can see that left hand side P and the N in the middle of the PMP system. So this physical length of the N region becomes shortened a lot. So there is a possibility for injected electrons would be alive at the edge of the N side. I mean here in at x of x prime c. I guess this is typo. You should remove one apostrophe here, and you should use two apostrophes for indicating the x direction on the p side. Anyhow, this is minor typo. Anyhow, so here x prime is xc prime, indicating the edge of the n side away from the depletion layer. Here the total amount of hole concentration at x prime of xc prime and delta excess hole concentration in the n side shouldn't become zero. Previously it was asymptotically approaching to zero, so we have used that delta p sub n at x prime of infinity is zero. That boundary condition has been used in ideal diode analysis. However, herein, since the physical length of n side becomes aggressively shortened a lot, so part of the injected holes would be still alive. I mean those electrons has not been well recombined with electrons in n side while it is going through the n side quasi-neutral region. So part of the injected holes are left to be alive. So we should negate this boundary condition. So instead of that boundary condition, we should use a delta p sub n, x prime is xc prime, should be something. Okay. All right. Okay. So with the following coordinate system, I mean that this x prime, x2 prime, the minority carrier diffusion equation, I mean the Pn round. I guess there is the full equation, no? Okay. The second order derivative is equal to delta p sub n divided by lp square. So to solve this second order differential equation or minority carrier equation, we're gonna write down the general solution first. So herein you can see that the general solution form given. So now the thing that we should do is to look for a1, a2, okay? So to look for the coefficient a1 and a2, we need two more boundary conditions, okay? So herein, at x of xn, that means here, x of xn, that is corresponding to the x prime is 0, okay? So that means when x prime is 0, how much excess holes are obtained. So delta p sub n under fold bias, I mean the certain amount of holes are injected into the n side, and at this edge, at x of xn or x prime is 0, how much excess hole concentration is available, okay? So that value can be defined by this constant, as we have learned in ideal diode analysis. If you still cannot understand how come this constant comes from, please go back to the ideal diode analysis and refresh your memory again, and you're gonna simply understand, aha, this value is very straightforward, okay? And second boundary condition is this. when we're doing the ideal diet analysis, delta p sub n at x prime is infinity, then we're gonna expect the zero. The nothing left at x prime of infinity. However, in this case, uh, the delta p sub n at x prime of xc prime, it is asymptotically approaching to zero value. So instead of infinity, we should plug in the xc prime. Where? When we are determining this coefficient. Okay, so that would make our life much complicated a lot. So let's take a look at it, how complex it is. So applying those two boundary conditions, we can have two equations. So the first one comes from, let's plug in the x prime of zero value here. 0, 0, and 0. Okay, then you're gonna get this. Okay, and second one is obtained from using this boundary condition. So you should plug in xc prime in the place of x prime. Okay, so here instead of x prime, plug in the xc prime. Okay, then you're gonna get this equation. Now, since we know this value and that value and this value, okay, so two unknowns, a1 and a2, and two equations, so definitely we can solve it. So you're gonna get the a1 and a2 by solving this two systematic equation, and then plug in a1 and a2 into the original general solution form here, a1 and a2. Then you're gonna build up this equation. Okay, definitely x prime should be in the range of 0 to xc prime. I mean the in p-n junction diode, uh, this regime. Okay, x prime is 0, here x prime is xc prime. Previously that was infinity, but now that is why we have used this expression. But now x prime is very limited between 0 and xc prime, because this physical dimension of n in the middle of PMP system is very limited. So x prime is xc prime. This is not identical to the infinity. Okay, so you can see that those very simplified part when describing delta p sub n as a function of x prime. So this guy, this second term, makes your life much complicated. So to make our life much easier, we can use this. We can take advantage of using a hypersine. Okay, so hypersine is defined as exponential x minus exponential minus x divided by 2. So this hypersine cosine is defined as exponential cosine minus exponential minus cosine divided by 2. You can convert the equation above into the equation below. Okay, so here in divided by 2, and this guy total divided by 2, and this, the only difference is there is a plus and there is minus, and this term and that terms are identical. So that is hypersine xc prime minus x prime over LP, like that. So you can find out the hypersine term here in. Okay, and here the total term is, plus, and that is minus, and xc prime over LP here, xc prime over LP, so that it can be described as hypersine xc prime over LP. Okay, so this term can be found here. All right, so delta p sub n as a function of x prime can be written as p sub n naught exponential QVA over KT minus 1. That is very identical to the very identical form that we have obtained and taken a look at ideal diode analysis. But second term has been added up. Okay. So please go back to the slide talking about the ideal diode analysis and compare the delta p sub n in the ideal diode analysis against delta p sub n in narrow base diode herein. Okay, so please compare two equations to each other. Then you're gonna see that this second term has been simply added up. Okay, all right, now let's do this. If xc prime becomes infinity, go back to this cross-sectional view here. If this xc prime becomes infinity, that means, let's get back to the original p-n junction diode analysis. Okay, the once hole is injected into the n side, and these holes would traveling the infinity length. Okay, so we're gonna get the same equation for delta p sub n in ideal diode analysis, same here. Okay, take a look at the conclusion. Yes, that's the equation that we have obtained in ideal diode analysis. So to confirm mathematically, this assumption would be still well valid. The equation that we have derived here in is still valid and still available for explaining the ideal diode. So for that purpose, instead of xc prime, you can plug in the infinity value into the xc prime. Okay, so here LP has been used for each xc prime and x prime, and we have rewrite those terms, and you may use this mathematics n over n plus 1. Once n is going to infinity, that is 1. Okay, so using this, you can simplify the equation shown in second line into the equation shown in the last line. Okay, and this value is the thing that we have obtained in ideal diode uh, analysis. Okay, all right, now this extreme case uh, has been explored. So how come this is very extreme? The base is super narrow. Base is super narrow means in PN diode, if this physical length becomes very tightly shortened a lot, this edge is described as xc prime. If this xc prime is asymptotically approaching to the zero value, what would be happened? Okay, so this equation is the same one as the equation shown in here. Yeah, this guy. Okay, it's just I simply bring it into this lecture note, and if this xc prime, this guy and that guy, asymptotically approaching to zero, how to simplify the equation? So I guess you need this as x is approaching to zero, hypersine x is also approaching to x. Okay, so since Xc prime is approaching to 0, this whole value, hypersine something, is asymptotically approaching to something, right? Because hypersine x is approaching to x itself. So you can just simply bring it out, okay? So in other words, you can simply erase hypersine, okay? Then we're gonna get each term are well placed on the right spot. Okay, then LP and that LP are canceled out to each other, and XC prime here and there are divided. So P and naught exponential QVA over KT minus 1 are still here, and this part has been rewritten as 1 minus x prime over XC prime. Okay, and here, to physically speaking, we can find out very interesting point. In PN diode, if this physical length becomes very aggressively shortened a lot, then the holes are, once the profile for injected holes are following the linear function instead of exponential function. I'm talking about this delta p sub n as a function of x, this guy. So hole under forward bias, hole is injected into the n side, and how much hole has been injected into the n side can be described with this term delta p sub n as a function of x. And this delta p sub n of x prime is blah 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 times exponential blah blah blah. Why was that? Yeah, go back to the long base case here. Delta p sub n of x prime blah 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 times exponential something. Okay, x prime, okay. This value is, kind of given constant. Once you apply certain amount of forward bias, this value is a kind of constant. Okay, so as a function of x prime, here exponential term can be found. So injected holes into the n side can be described mathematically with exponential term. So if I draw the delta p sub n x prime 0, that point is x of n, the depletion layer h. That value described as like that, not straight line. However, this physical length of the n side becomes aggressively shortened a lot, then the curve looks like that. But in the end, it should like it looks like a straight line. Okay, so in case of narrow base, mathematically speaking, xc prime becomes asymptotically 0. This excess hole concentration, excess minority carrier concentration in the n side, right? Delta p sub n as a function of x prime can be described blah 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 exponential something, but instead of this guy, blah 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 times 1 minus x prime over xc prime. This is a linear function. So this physical length of n side becomes very very small, very very short. We can describe the excess minority carrier concentration with a linear function of x. Okay, so as described here, delta p sub n is now becomes a linear function of x instead of the exponential function of x. Okay, what does it mean? Delta p sub n is linear function of x. What does it mean physically? In ideal diode, many holes are injected into the n side, and this hole concentration profile is following the exponential term. What does it mean? Delta p sub n x prime is blah 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 exponential something x prime. Think about the second step of the ideal diode analysis. If you have forgotten all the ideal diode analysis, please stop here and review what we have learned in ideal diode analysis. There are three big steps. Step number one was to derive the minority carrier concentration, excess minority carrier concentration in each side, p side and n side. And second step was to write down the current density in quasi-neutral region. Because in the quasi-neutral region, the electric field is zero, drift current component has been gone, so the diffusion current, maybe here in the hole is now diffusing in the n-side, diffusion current by hole has been written as unit charge times diffusion constant times delta p sub n divided by round density. So in the second big step in ideal diode analysis, that was kind of more or less very simple. In step number one, once you well derive delta p sub n, just in the second step, plug in this current density equation and take a first derivative of it and the multiplying q and dp. That's it. That's all your job in the second step. Afterwards, in the third step, we're gonna define and derive the total whole current density by defining that the diffusion current component at the edge of the n side is identical to the diffusion current value at depletion region at p side. I mean, the no recombination has been happened across the depletion layer. So using that basic concept, basic assumption, we can derive the total current density across PN diode throughout the PN diode. Okay, so that was the last step in ideal diode analysis. So please refresh your memory again with ideal diode analysis, three big steps, and go back and come back to this point. Okay. So suppose that you are well geared up with a basic knowledge on ideal diode analysis, then now, since delta p sub n is described with a linear function of x, so here in delta p sub n is blah 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 x prime. So plug in here. Once you take a first derivative of first order equation, this term becomes constant. Whatever the additional terms are multiplied to the constant, the result is still constant. So the whole diffusion current density becomes constant. So that is the main reason I have written down here JP is constant. Well, but definitely the basic assumption is there is no recombination happened. Okay, so let's do some more detailed work. JP is defined as, here, minus Q times dP times, excess hole concentration in the n side. So we should take a first derivative of it. Okay, so in case of narrow base, the mathematical job is very simple because delta p sub n is following the linear function of x. However, in case of long base PN diode, delta p sub n is described with an exponential term. So, but instead of this term, let's use the full original equation, this guy. But instead of this guy, in the previous slide, let's use this equation for delta p sub n. So this delta p sub n is original one. Okay, in ideal diode analysis, this hypersign term and those second terms are removed. But in real and more general diet analysis, this second term, hypersine term, should be considered together. So let's remember this whole more general equation for delta P sub n, excess hole concentration in the n side. So please remember it, and let's take it and bring it into here. So plug in and take a derivative of it and multiplying minus q times dp. So how to take the derivative of hypersine? So just for your information, hypersine, let me see, yeah, there we go. Hypersine is defined as exponential psi minus exponential minus psi. So take a first derivative of hypersine. What would becomes? Yes, exponential psi would becomes exponential psi, and this guy exponential minus psi. So take a first derivative of it, minus would becomes out, and plus exponential minus psi. So this term, this whole equation can be defined as hypercosine psi, which is also described here. Okay, so d dx hypersine x is equal to hypercosine x. Okay, so using this concept, you can derive it, and you're gonna end up with this equation. So please do that. I'm going to give you out the homework to fully describe how to get this equation. Okay, so JP is described with this very complicated equation. And in the Beer's book, the author has used this assumption for a P plus N junction. So many holes are injected into the N side, okay? And the electrons would also injected into the P side. However, this amount is very, very small compared against these injected holes. So we're gonna ignore this term. So the current flow across P plus N junction is defined as this. JP is a current density. So by multiplying a cross-sectional area, we're gonna get the current. So current is cross-sectional area times J sub P, where at x prime of 0. X prime indicates P plus N junction depletion layer. So at the edge of the depletion layer indicates x prime c, which is identical to the x is x of n. Okay, so the equation above here, just plug in the x prime is 0. So here 0 value, okay. All right, then the minus and this minus are cancelled out, and 1 over LP has been moved in this section. So Q dp LP, Q dp LP, and A comes from this, okay? And the P sub n naught. P sub n naught is, at thermal equilibrium in the N side. How many holes are available? That means in the antimaterial, the minority carrier concentration. So this guy is Ni squared divided by N naught. And using mass section law, definitely. So Ni squared over N naught is identical to the donor's concentration in the N side of PN diode. So you can see that ND, Ni squared, right? Instead of PN naught, I have used the Ni squared over ND. And the exponential stuff, exponential QVA over KT minus 1 are simply moved downward here. And here hypercosine and x prime is 0, so xc prime over LP here. And here hypersine xc prime over LP. That term has been moved as it is. Okay, and now since the total current flow across P plus N junction can be defined with this equation. And now, depending on the bias that you have applied, is critical one in determining the current flow in P plus N junction. So the other terms, this whole other terms are combined together and described as I naught prime. Why I naught instead of I naught prime? Because hypercosine, hypersine terms are additionally included in I naught. So go back to the ideal diode analysis. You can see the I naught exponential QVA over KT minus 1. Okay. So previously we have used the I naught as a saturation current, but now more generic form of I naught, that is I naught prime. So here I naught prime. Previously only this part has been left in P plus N junction. Okay, P plus N junction. When we are learning the simple PN junction diode, then you're gonna see that another one Q, I naught was QA dP LP ND NI square plus QA LN DN NA NI square. But now this part, this term has been removed because the electrons are negligible amount of electrons are injected into the P plus side. So this second term has been removed. So the first term has been left. But now more terms, single term has been included in the saturation current as I naught prime. Okay. So basic form of diode equation are still well kept. However, some more detailed terms are included in this I naught prime. So current flow I in P plus N junction is I naught prime times exponential QVA over KT minus 1. So this is really the same format of the ideal diode equation. However, I naught prime becomes more complicated with the hypercosine, hypersine terms. Okay, and in this lecture note, more deep understanding on I naught has been provided. So the second term, this guy, hypercosine, hypersine. Going back to the previous slide, I'm talking about this part. Okay, so this part can be approximated if Xc prime is much shorter than Lp. That means in P plus N diode, 0, X prime is 0, this X prime is Xc prime. If this Xc prime is much shorter than Lp, Lp means a diffusion length. So the meaning of diffusion length is, again here, the average distance that the minority carrier can survive without any recombination with the majority carrier. Simply speaking, once a hole is injected here, how long it can be traveling without recombination with electrons in inside material. So that concept, physical length, average physical length of injected holes to be not to be recombined with electrons in inside is defined as a diffusion length. But this Xc prime, I mean from here to here, the length is very short, even shorter than one single diffusion length. Then this hypercosine hypersine term can be simplified. Previously I said as cosine is approaching to 0, hypersine cosine hypersine becomes a linear, just a cosine. Okay, what about the hypercosine as cosine is asymptotically approaching to 0? Yeah, go back to the mathematics and calculus class. You can see that this. Okay, so you can simplify this equation like that. Okay, so that has been here, and this guy has been here. All right, and from here to here, let's do this. Multiplying LP on both sides. Let me erase it. Here times LP, and here times LP. Then XC prime, this is LP prime, XC prime square divided by LP. And now LP is much longer than XC prime. I mean, this condition is still valid. So XC prime square divided by LP should be 0. I mean that this value should be very small. So LP over XC prime is left. Okay. Now let's do some more simplification. Previously I naught prime. Let's go back to the original form for I naught prime. This guy, right? I naught prime is this, but this part has been approximated as XC prime LP. Okay, so I naught prime becomes the equation shown in here, and LP are cancelled out. Okay, and you're gonna end up with this equation. All right, we're almost done. So in narrow base diode IV equation, so now you may understand that the meaning of narrow in PN diode, the physical length of the quasi-neutral region of N side, this physical length is very short or narrow, then how the current is flowing for given bias voltage. So we're almost done. Here, anti-Brisson, the width of anti-Brisson is defined as Wn. So physical anti-Brisson is defined as Wn. But there is a depletion layer included in the N side, right? So I mean that this is x of 0, this is x of xn. So the quasi-neutral region of N side is defined as Wn prime, and that is defined as Wn minus xn. Okay, so this. And this Wn prime is, what if this Wn prime is much shorter than single diffusion length? Then we're gonna write down the current is defined as I naught prime times exponential QVA over KT minus 1, as we have done in ideal diode analysis. But here notice that I naught prime is QA squared dP over Wn prime and d. Previously we have focused on P plus N junction, but in this lecture note I have included this part. The electrons should be injected into the p side, so this part comes from or make contribution this equation. Okay, all right, so I guess let me see. In summary slide, long N side and long P side, by combining those two, long P side and long N side, this is very long and that is very long. This is the ideal diode, right? Then I naught saturation current value is QANI squared times dP over LPND plus QANI squared dN over LNNA. Okay, so by summing up those two terms, you're gonna build up the I naught value for ideal PN diode. So go back to the ideal PN junction diode analysis again and confirm that I naught value, saturation current value, consists of two terms, this and that, this and that. Please do that. what if this n side is very short? Then for given bias voltage, how much current is flowing and what is the saturation current? Take it this, long p side plus short n side. What if this p side is very narrow, n side is very long? Then for given bias, how much current is flowing and I naught exponential QVA over KT minus 1. But this I naught, how to get it? Yes. Now P side is very short. So short P side, this plus long N side. Yeah, this. Okay. So simply add two terms from for each N side and P side. You can build up the saturation current component. Okay. So this summary slide is well describing how to get or how to build up the saturation current equation, I naught. Okay. So previously, when we are doing the ideal diode analysis, that was originally long p side plus long n side junction. But what if either side of p-n diode has been aggressively shortened a lot, even shorter than one diffusion length of minority carrier? Then we should go back to this lecture note summary slide and take out the appropriate terms. Okay. What if both sides are very aggressively scaled down, short N side and short P side? Then your saturation current I naught consists of two terms. Which one? Yes, this plus that. So that is well written here. This plus that. Okay. But still, the original form of the ideal diode analysis has been well kept. So this is a, kind of advanced topics. However, I hope all the students who are taking my lecture to catch up all the detailed analysis that I have explained in this movie clip. So this movie clip is kind of long, but please keep an eye on how to derive the generic form diode IV equation. And the key knob is found in saturation current I naught. So I guess that this summary slide is a good spot to build up the appropriate saturation current for a given diode, whatever it is, long P side with a short N side or short P side plus long N side, whatever it is. You can build up the right equation for saturation current I naught. Okay. All right, so I guess that's all for today's lecture and see you in the next movie clip. Thanks for your attention. Bye bye.